Okay, well, good morning, everyone. Thanks for joining me this morning. I hope you had more coffee than me, so try not to be too boring. So today we're going to talk about indoor air quality and how it relates to buildings and what we can extract from IAQ data using data analytics and machine learning. So I'm going to cover different topics. I guess these are very interesting slides. Okay. So my name is Julien Stamatakis. I'm a CTO and co-founder of a company called Attune. My background is in biomedical engineering and more particularly doing networks of sensors to help detect Parkinson's disease. And now I'm diagnosing buildings, so a little bit of a change, but indoor quality. So you may or may not know that monitoring indoor quality is important because it has an effect on our health. There's a lot of papers on that, more and more pollution, smoking, all that stuff is bad for you. And so since we spend a lot of time indoors, it's interesting to monitor air quality indoors, just like we do outdoors. And the field of indoor quality monitoring has really been put to the forefront with COVID, right? A lot of people started wondering, okay, spend all this time indoors with other people, how does that affect us? Is the air inside building safe and whatnot? And one of the things that ASHRAE said at the time, I mean, they're still saying it, but is that the best way to mitigate and remove virus pathogen is through well-operated HVAC systems, which include ventilation and filtration. So during COVID and post-COVID, what I was talking about and what I was presenting was all around how do we develop confidence that the space you're in are safe, and how to manage the building to keep the space safe. So what a lot of people did was, increase ventilation, bring more outside air, increase size of filters, all that stuff. And now, 1-2 years later, the next question is, well, all that at a cost, right? All that has a huge cost in terms of energy. And now the question is, well, we spend, decades trying to reduce energy consumption, and now we threw everything out the window trying to improve air quality. How can we live in a world where we balance both of those things? And so that's kind of what I'm going to try to talk about today. The answer is it's not easy. And so we're going to look at three aspects, 3 case studies, I don't know what to call them. So ventilation and CO2 levels, filtration, efficacy, and then how machine learning can help us with those type of analysis. So what I'm going to talk about today is based on data from different types of buildings, Class A, commercial buildings, schools, stuff like that. And before I go there, and I found a super feature here. So it's where we put the sensors. So there's 4 places where usually people put sensors in buildings. The most obvious one that a lot of people do for well and whatnot is, in the breathing zones. Just like we put on a wall here. But what a lot of people do is more the core and shell approach, which is putting sensor in the supply air, the return air, and the outside air, right? Because that's the base of your HVAC system. You supply air to the space, people breathe it, it returns into the system, gets mixed with outside air to try to bring some fresh air, and then the loop continues. So that's just to know what I'm going to talk about. So the first thing I'm going to look at is ventilation and CO2 levels. As we breathe, we exhale CO2. If we never bring outside air, we'll all fall asleep and end up, I wouldn't say dying, but in a very bad shape. Because we're just going to keep breathing that same air. There's going to be less oxygen. So that's why we bring outside air. And during COVID, to try, we didn't really know what was going on, to try to reduce the chance of breathing someone else's air and the virus, we just said, okay, let's bring 100% outside air so we don't rebreathe other air. And that was an approach. The other approach was from before, which is, okay, we want to save energy, let's not bring any outside air because we have to condition it, it's expensive. And so, the question is now, where do we sit in that balance? Because, as most of you may know, HVAC systems are not designed based on air quality, they're based on temperature. So, just to give you some data, I don't know if you guys are familiar with CO2 data or whatnot, so I just want to, kind of level set things and show you different buildings and, what the trends look like. So on this one, I have a commercial building class A in Washington, D.C., and we looked at different floors. So average CO2 is below 600 ppm. So outdoor air is 400, give or take, ppm. That's considered fresh air. And so if you have no occupancy in a building, you will have those levels. And so if you reach between 1,000 to 1,200, that's where you start, it start not being great. So here, 600 is great. Maximum CO2 is 1,000, great. So that's monthly average for building. Then we look at a school. A school is kind of the opposite of a Class A building. A lot of schools are, they don't have outside air because, they were not designed for that. It's old buildings or they're portables. I don't know. They're just the worst type of buildings, unfortunately. So here, if you look at the average CO2 over a month, also 100, 600 ppm, that's great. But then if you look at the maximum CO2 level, that's so much higher. And it's very small, but it's like 2,000, 3,000 ppm, right? So the kids breathe that, and it's not great. Here, we look at the daily averages. And we see at the top, it's the commercial building, the difference between, the non-occupied space, non-occupied time and occupied time is only like 350 ppm extra. And, the kind of, I'm not an expert, but the old ASHRAE recommendation was 700 ppm above outside air. So here we're kind of way below that. But in the school, we're 720, right? So this is like already a difference. So now if we look at return air versus supply air. So the assumption would be, okay, my supply air will always have less CO2 than my return air because I'm mixing in outside air. If they're the same, it means I'm not bringing any outside air. Okay, so if we look at one of the days with higher CO2 in a commercial building, we see that the trends are the same. So it makes sense. I have higher CO2 because I'm not bringing outside air. Makes sense. In a school, which is the bottom graph, I know that in this particular school, there's no outside air, right? So it's, we don't have supply air, we have breathing zone, so it's a little bit different, but same. The trends are very similar because there's no outside air, but now the level is so much higher. I think they're, I can't read, like above 2,000. So we start seeing, okay, the outside air matters. On a low CO2 day for the commercial buildings, we see that now there's a big difference between supply air, return air. So we bring outside air, the CO2 levels overall are much lower. Makes sense. In the school, the space are much smaller and there's no outside air. So you can see how the CO2 spikes and goes down so fast. That's how, just having people in the space brings those levels very quickly. And one of the things that you may have heard is the air exchange per hour. It's like how fast can you replace the air in a room? And that will impact that slope that you see. So when you look at those trends, the the slope, the slope, if it's very sharp or not, actually shows you an image of how well your ventilation is running. So based on that data, we can create additional metrics. Here as an example that we call ventilation score, and it's basically going to look at how fast the contaminants increase or decrease in a space. And that gives you an image of how well the space is ventilated, right? So here in this space, if it's well ventilated, I would expect the CO2 to rise because we're a lot of people, but rise slowly. And then as soon as we all leave, it's going to sharply decrease because the system works. If it doesn't, then I know the ventilation system doesn't work. And so the CO2 is not the only contaminant, right? The other contaminant, and that's also got highlighted with COVID, is the PM, particulate matter, and the VOCs. So VOCs for COVID was really related to cleaning products, right? Because a lot of disinfectants and cleaning supplies that we use during COVID to disinfect stuff had a lot of bad VOCs in it, and it's really bad to breathe them. And for particulate matter, it was related to actually spreading the virus on droplets that you're breathing. So those can also be incorporated in those ventilation score and how well the ventilation can remove them. So enough talking about background. Let's look at actual data. So I'm focusing on the classic commercial building. And the question is, okay, is the ventilation performing properly based on the level of occupancy, right? Because if you say, okay, I'm bringing 100% outside air, it's great. If there's a lot of people, okay, maybe. If there's no one in there, why bother? It's just wasting money. So the problem is that it's really hard to know how many people are in a building. It's like not a metric that people used to monitor because it was, okay, try to have your building occupied all the time. But with COVID, everybody working from home, you have no idea how many people are in your building, right? Especially the building operators, if they have tenants, how do you know when the tenants are there? So I don't know if you do, but we get emails all the time. Oh, how many people are back, to coming to the office every day? Stuff like that. They're trying to figure it out. So in this case here, we were able to get occupancy for the whole building just by people swiping their passes. So that's the blue line. And then in orange is the CO2 levels on the return air for one of the floors. And so just looking at the data, we see, okay, there are a couple of days where it's weird. There's like more CO2, but less occupancy. Could be totally, by chance, all those people were actually on that floor. We don't know, but that's, a starting point. So the question is, can we just, with the data we're getting, figure out why it's happening? So first thing, we do just like a correlation. We see, okay, those points are, coming out. Okay, that's great, not very useful. Then we start thinking, okay, how does the HVAC system work? How does it decide I'm gonna bring outside air or whatever? It's based on temperature, right? So it's actually looking at the amount of energy it needs to use to cool down the outside air. And if that's a lot, the system will decide, okay, I'm not going to bring outside air, right? Because I'm going to spend too much energy, too much money doing that. That's how the system thinks. So we, with all the sensors we had in the outside air, return air, supply air, we started calculating the enthalpy of the outside air, return air. Put that together here. So just to give you an idea, so the blue line, I don't know if you can see, is the supply air CO2, yellow line, return air CO2, orange is the enthalpy of the return air, and purple, the enthalpy of the outside air. So basically, if the purple is above the orange, it would not bring outside air, and if it's the opposite, it would, just to give you an idea. That's how the system behaves. Does it relate to CO2? Not at all. So we plotted the data in a way to try to detect those anomalies. So what is anomalies? Anomalies is when my supply air CO2 is close to my return air CO2, meaning I'm not bringing enough outside air, and my return CO2 return air CO2 is high, right? That's anomalous. And I found in this data set here, I have 2 points that behave that way. Believe it or not, it's the 2 days we found, on the initial graph I showed. So we're on the right track. Then we plotted them in a way where we look at the difference in enthalpy, right? So on this side, the outside air enthalpy is higher than the return air enthalpy, so we would not bring outside air. And vertically is the difference between supply air and return air CO2. So if we are above here, we don't bring a lot of outside air, and at the bottom, we bring outside air. And then in red are the points where the return air CO2 is above 700 ppm. And all the points that are in this quadrant, which is I don't want to bring outside air because my enthalpy for my outside air is too high, and I'm actually seeing that there's no supply being brought. All those points are here, and those are the days that I found. So basically, long story short, if my enthalpy from the outside air is too high, the system will not bring outside air, and those are the days where we see we have much higher CO2 than usual. So it clearly shows that the system should be smarter than that. And okay, there is, it costs energy to bring the outside air, but, what's more important, my energy bill or the, comfort of the people in the space? In this case, the high CO2 level were not that high, was 700 ppm, so it's not bad, but it gives you an idea of how the system behaves and how we should change it so that it not only look at, temperature, it also looks at CO2 levels to decide how it operates. And, now you guys are expert, maybe new buildings starting to look like that, but every existing building, schools included, don't behave like that at all. And so by doing this, we can start optimizing energy consumption versus air quality versus, shooting in the dark and saying either I'm running things the old way where, I don't care about CO2, or saying I'm just really overriding the system and saying X% outside there all the time, which doesn't make sense either. So we did the same thing on another building just to see if that, approach works. So in this case, we had, not really couldn't really see anything on the occupancy versus CO2 level. The correlation, nothing really stood out. So we just did the exact same analysis, calculated the enthalpy of the return air outside air, plotted in this graph, and looked at, okay, which are the days where my return air is above 700 ppm and there's no difference between supply air and return air CO2. Found 3 days, plotted it in the same type of graph, and again, all the points in the top right quadrant are those days where I have problems. So we only did 2 buildings, but it's clearly an indication that that's the way to go. And so now the question is like, what do we do with this information, right? Because we install those sensors, I do the analysis, I can fix the problem. So we need to close the loop. And in this case, we're working directly with the building engineers to give them this information so that they can go and tweak their systems, now that they have access to this information. The other issue is that these sensors are not especially tied into the BMS, but now it's possible to send that data back into BMS as well, so they can incorporate that in the rules versus doing it manually. Yeah, so that was saying. So it's closing the loop with the engineers is the next step for those buildings where we install sensors. A question we also often get is, okay, with the CO2 data, can I extrapolate when there is occupancy or not? And so that's not really for, a place like this. It's more like for, smaller offices and to know if they're occupied, right? Because with COVID, people downsized and try to have like individual workstations that you can reserve, go work, and whatnot. And a lot of times people reserve it, don't show up, and they need more space than you actually need. So we use the CO2 sensor, place them in those offices, and try to detect occupancy just based on that. And what we saw is that it really does work, again, based on those slopes, right? So if there's a sharp increase in CO2, there's someone in there, you don't know how many people, but there's someone there, and then when they leave, you'll see that decrease. But what we also notice is that because when there's no outside air, you recycle, basically the air that's in there, you can have people present in other spaces, and all that air is mixed together and sent back into the space. So you can have CO2 from another space suddenly feeding into an empty space. And so in the bottom graph here, you actually see like false positive where there's actually nobody in the space, but the CO2 levels increase because there are people in other spaces. So that was an interesting finding, and it really shows that people breathing in one area really affects others. And so for it to really work well, you need to calibrate kind of those slopes based on the space. But it does work, and we're able to kind of show when the different offices were occupied and whatnot, and correlate that with actual presence taken physically. So it was just a little side note. And so, answering the question, are we overventilating? Are we bringing enough outside air? Yes, that can be answered just looking at the data and incorporated into new procedures for HVAC operations. One thing that we're hearing more and more is trying to get that granular level of occupancy as well. And so you'll see on the market more and more occupancy sensor that try to tell you, within a specific space, how many people are present at a certain amount of time, a certain period of time. I'm hearing a lot of people trying to use it. I don't know if you guys have seen, people actually implementing it. I'd be curious to hear about that. It could be a bit tedious to install because you have to put it, like above each door. Like for example, here where we need like 5 sensors versus like an IAQ, you could just put one. But we're seeing a lot of that to try to add an extra level of information. So now I talked about the ventilation. So the other big aspect of what changed with COVID is filtration. I'm going to go back to kind of the basics. I don't know if you guys know about filters, but hopefully it's not boring. You learn something. But the questions are, are the filters I'm using good enough, and when should I change them? Because with COVID, people try to go to higher MERV rating filters to filter more particles. Those filters are more expensive, so people tend to change them less often, but that has an energy cost. Because as the filters get, higher rating, they're kind of tighter, it takes more energy to push the air through them, and as they get dirty, it gets even worse. And so I'm sure you've all seen this graph by now. It's basically the filtration efficacy based on the MERV rating. So you would have, here at the bottom, like the worst, MERV 4, and you see that, at best, it filters 10% of particles. And then, at the top, you'll have a MERV 16, which filters like 100% of particles down to a certain particle size, and then it starts going down. So you see that all the graphs drop just below 0.3 micron, and that's just because the way particles behave at that size, it changed. And so it just much harder to filter at that particular size. And problem is that a lot of the viruses and droplets that we expel are in that 0.3 to 1 micron range. And so unfortunately, they're harder to filter. And so that's why people try to move to higher MERV rating to try to capture as many particles as possible. And you see, here it's like 70% efficacy, right? For the best MERV filter, you can only achieve 70% filtration efficacy at that particular size. So it's not perfect. And then, so before COVID, you would see, MERV 8, MERV 10, and you see MERV 10 even, at larger particles is still 90% efficacy. And so that's really why that jump really makes a difference between a 10 and a 13, which is from here to here. In terms of particle size, so you always hear, PM 2.5, PM 10, whatever. So what does that actually mean? It's important to know. So your PM1, the way we define it in the sensor world, is basically your particles from 0.3 micron, and I explain why that's a number that exists, to 1. But then your PM 2.5 is not 1 to 2.5. It's also from 0.3 to 2.5. And then your PM 10 is also going to be 0.3 to 10. So it's always inclusive of the whole range. It's really important to know because it matters. So if you want to know your 1 to 2.5, you have to do the difference between PM 2.5 and PM 1 to just get that range. So I read about PM sensors because I realized that a lot of people don't know how it works, and it's really, really important. So I'm not talking about like super expensive gravitational sensors that cost a fortune. I'm talking about low-cost sensor you'll find in any type of air quality monitor that you find on the market. The way it works is that you have like a duct, and then you have a laser. Laser sends the light. As the particle pass, the light gets scattered, and then there is a sensor that measures the intensity of the scattered light. And based on that intensity, it will determine what's the size of the particle. Okay? You see on this graph here, in the middle, this kind of like, I don't know, ghost kind of shape, that the intensity of the scattered light depends on the angle at which you measure that intensity. So that matters. It means that wherever you're going to put that sensor will matter. You have to calibrate it. So there are 4 things that are really, really important. First, the airflow. Because you're measuring at a specific location, you need to make sure you can cover what's going on within the room. So you need a fan that's strong enough and a duct that's big enough to bring the air from the room, let it go through that kind of ductwork. It's really small, but I'll call it the duct, to get a good representation of the particles in the space. If you have a fan that's really cheap, it will not pull a lot of air, and you will feel like, oh, my air quality is great. Well, yeah, it's because you're not sampling anything. So that's really important. And then when you look at specs, you will say, oh, it does PM1, PM2.5, PM10, let's buy it. No, you have to go deeper in the sheet and look at what's the airflow for the sensor. Then the second one is the scattering angle, right? As I was saying. And you can see actually on this graph here, it's the intensity of the scattered light based on the particular size for different sensor angles. And why it matters is, for example, you look at the yellow line, which is like a 150 to 170 degree between the laser and the sensor. You see those, whatever it's, ripples or whatever it's called, waves. What it means is that if you measure this intensity, it could be a 1 micron particle or a 4 micron particle. How do you know which one it is? You don't. So the angle matters. What's better is having 2 sensors, because then you know for sure what's the particle size, right? So again, it matters. It's 1 sensor, 2 sensors. It will greatly improve the accuracy of the sensor. Third one is the laser wavelength. So the laser has a specific color. For example, a red will have a 660 nanometer wavelength. And not bore you with physics, but basically you can detect particles 1x to 10x the wavelength. So if you have a 660 nanometer, which is 0.6 micron, you can detect particles 0.6 micron to 6.6 micron, okay? And that's why with those sensors, and red is the most common, you will kind of go down to 0.3 maybe, right, micron, and kind of maybe up to 10, but really the good range is 0.6 to 6.6. You can have a blue wavelength, which is, I don't remember, lower than that. And so for those, you can go, I think it was like 0.16 micron to 1.6 micron. So I don't remember the exact number, but it's smaller. So you can detect smaller particles. Sensors who say, oh, we could do 0.1 micron detection. Well, check what color of the laser is, because if it's red, it's not true. It's most probably just extrapolation or whatnot. And then if they do that, then they will be very bad at measuring 10 micron, right? Because they go outside of the range. The best laser would be a white, because it covers all the colors. It's crazy expensive. So most probably you will not find it in an instrument. Lastly, humidity compensation. So as air gets more humid, particles will stick together. And so you will have a kind of false reading of the true distribution of particles, because you will suddenly read a lot of big particles. And so good sensor will have like a heating element, for example, that will dry the air before it goes into the system, so that you actually read the correct particle distribution. So you guys tell me, who looked at all these things the last time they bought a PM sensor? I don't know if you're not listening or nobody did it, but I'll take it as nobody did it. So it's really important. And that's what we used. So let's look at some of the data. So this is in another building. I don't remember where it is, but it's also Class A. And they used a MERV 14 filter on the outside air, and they put the sensor after that. And what we see on this graph is that the three numbers are the same. What does that mean that the three numbers are the same? It means that all the particles are between 0.3 and 1 micron, right? Because you do the difference if you want to do the bins, you would have 0 from 1 to 2.5 and 0 from 2.5 to 10. So it makes sense. They have MERV 14 filter. All the particles that don't get filtered are in that first bucket. And so then what we did is, in this particular building, they always bring 25% outside air. It's kind of like a fixed ratio they have. And then we looked at the filtration efficacy, which is basically how many particles go through the filter between the return and supply air. And we looked at that at different floors. And what was really interesting is that because they also use MERV 13 filters on their HVAC units, the filtration efficacy was almost always 100% for their PM 2.5, PM 10. And in this case, I actually made the difference. Should have called it differently, but it's 1 to 2.5 for this graph and 2.5 to 10 for this graph. What it tells us is that we can use this data to know if you have leaks in your filters, right? So when you install filters, sometimes they're not sealed properly, and then you would have particles go through. So if you have a good MERV rating filter, if you see anything that's not 100%, you know you have a leak and you can go plug it, because it's really hard to do otherwise. The other interesting thing we found is that as time goes on, the filters get dirtier. And actually the impact of that is that your filtration efficacy increases. Because as it gets dirtier, it's actually even harder for particles to go through, and so your filtration efficacy goes up. And so it's kind of counterintuitive in a sense, right? You would say, okay, well, my filter is bad, doesn't filter well, I'm going to change it. No, it's kind of the opposite. So when your filtration efficacy kind of plateaus, it means that your filter is dirty. What we're missing, though, and we're starting to do now, is go a level further than that and actually tie that to energy consumption, right? To see, okay, as my filter gets dirtier, what's the impact on my energy consumption? And we didn't have the data for this set, but hopefully for next year we do. But that was a really interesting finding. Then we kind of tried to do that for the school I was talking about. Different story. So that school in question doesn't have outside air. Well, what does it have? Very poor insulation from the outside. And so as there were events outdoors of PM, like higher PMs, we actually saw the impact on the indoor air quality. So all that dirty air from the outside was directly, coming through the doors and cracks and stuff and impacting the air indoors. And so that's where, even though they don't have outside air, having really good filtration in their units does matter, and it's really the only thing they could do. They can also use portable air filters, like the EPA, whatever station you could put in, that will really reduce their PM, and we see a lot of schools do that. And so so for the filtration efficacy, we can see directly with the PM data the effect of what MER filter they're using. The next step we need to do is really tie that to actual energy consumption and the impact of changing the MER filter. So going from a 10 to a 13, what's the impact on energy consumption? And then as the filters get dirty, what's the optimal time to change them? Because if you leave them longer, you will save on cost for not changing the filter, but you will have an impact on your energy. And we're working now on finding the optimal time to change it based on those two factors. Now the reason why you all came here, machine learning. Who knows anything about machine learning here? Okay. Okay, so very simplistic. It's not ChatGPT. It's very different. I don't know how ChatGPT works, but I know this works. So it's basically trying to figure out what points are most different than the others, right? So we're really using it to do anomaly detection or classification of when is there something weird happening in my building based on the IQ data. And it could be for a lot of things, right? It could be, like we talked about before, because my system is designed on temperature and doesn't look at CO2 and I have CO2 events, and I actually want to see if I could detect that automatically versus having to do all the analysis I was doing earlier. So a few things. So that's really the goal. It's figuring out what points are different in the data set compared to the others. And then there's different techniques to do that, and I'm going to go through a few techniques. So one is just clustering, right? So you have all these points trying to see, okay, this group is there, it's normal, and then we have this group over there that's different. That's clustering. We could dimension reduction. It's basically, imagine having like a cloud of points, but not in 3D, in like, whatever, 100, 200, 1,000 dimensions, and trying to look at it in a way where you can clearly see two different clouds in a way, right? It's like looking from a very specific angle, and then at that point, you can just try to extract features that show you that view from that angle, and then you can separate them. And then the last one is supervised classification, which is basically your data set in advance, your training data set, and then you say this point is good, this point is anomalous, and then you train the model on that, and then you feed it new data, and the model will tell you, okay, this is good, this is bad. And so that difference between, that's the supervised way, and the first two I was talking about are unsupervised, where you don't know in advance what's good, what's bad, and you have to kind of figure it out or let the system figure it out. The difference between the two, so it's basically called supervised learning and unsupervised learning. So supervised learning, you tell the system in advance on the data you use to train the model, which is good, which is bad, and then the system will create a model, and then you feed new data, and it will tell you. Unsupervised, it's you don't know in advance. And that's our case, because not a lot of people can look at the data and tell you this is normal, this is not normal. And that's a huge challenge now that we're trying to solve, is the building engineers, the people who operate the building have no knowledge of air quality. It's not their expertise, it's not their field. They never were trained to look at it, and now suddenly we dump that data on them, and they don't know what to do with it, right? So we're kind of falling in that unsupervised learning category, which is actually much, much harder, because the system needs to figure something out, and then we have to tell the system, does it make sense or not? And so even with unsupervised learning, after that, you need to try to figure out, okay, does it make sense or not? It's not always easy. So a lot of preliminary work when you do machine learning is just data cleaning. I mean, anybody who does data analysis knows that. Data cleaning, filling up gaps, normalizing data, extracting the data for operating hours versus whole day makes a difference. So the first method I was talking about is that dimension reduction, which is trying to, from the temperature, humidity, CO2, from supply air, return air, CO2, like you have so many stuff, and then you can correlate them, you can add them, you can subtract them, like all that creates another dimension, if you will. And then the dimension reduction is trying to find which one of those dimension or metrics makes sense to separate the good and the bad, okay? And in some cases, it works really well. In our case, it didn't work at all because we lose so much information that just doesn't work. It's too complicated to be simplified this way, in a sense. So that didn't work at all. Then we tried something that's called the clustering with an algorithm called dbScan. And that was interesting. It was useless, but it was very interesting. It basically, the system was able to cluster the data in one cluster was Monday, Tuesday, Wednesday. The other cluster was Thursday, Friday, Saturday, Sunday. It's totally useless, but it was interesting that the system was able to see that there was a different pattern in the HVAC system between the first 3 days of the week and the last 4 days of the week. Probably because occupancy is different. Earlier in the week, more people go to work in the space, and then Thursday, Friday they don't. So it looks more like a weekend. But that gives you kind of an idea of what the system can do that no one looking at the data would have been able to do. But as I said, that was useless. That's not what we're looking for. So the next technique we tried was autoencoders. So autoencoders, basically, you try to, how you have like a cloud of points and you try to run like a line or curve through it to kind of approximate it. But it's the same concept. You have, your curve, you try to reduce the dimension of that line. So let's say you have like something like this, you try to do a curve like this, and then you try to reconstruct the initial curve, the initial line, and then you look at the error between what you had and what you estimated, and the bigger the error, the more probable you have something strange. And so this picture kind of shows it well. You have that number 4. You try to draw that 4 with a lower dimension, and then you try to reconstruct that 4, and then you look at the difference between the two. And so the model will kind of be able to reconstruct it really well, but then when you feed it new data, you will see how that new data differs from the reconstructed model, if you will. And so doing that, you have like some good example of curves where, here, this one is good. So the blue line is the actual data, and then the orange is kind of that simplified version, like the lower dimension, and then you look at the difference between the two. You see that it really follows the line really well, right? So the model is good, but then when you feed it new data, you look at, now, okay, does it still fit well that curve or not? And if not, it might be an anomaly. And so when you look at the histogram of distribution of the difference, everything that's too high of a difference is obviously not out of point because you expect not a lot of anomalous data points. You draw kind of that limit, and then all these points are considered anomalies. Are they anomalies or not? You don't know. And that's the problem, is that how do we know? So it works really well for CO2, doesn't work too well for particulate matter. See, I'm kind of running out of time. So doing that, we were able to find some anomalous days. And really the issue is that we do all these data analysis, but we lack what I was saying about unsupervised learning. Does it make sense or not, right? So all that data goes back to the building engineer, but the building engineers, oh yeah, like 2 weeks ago, did you have a problem? They have no idea. They don't really track that information, especially if it's related to air quality. Was your CO2 too high 2 weeks ago for whatever reason? They don't know. And so that's the kind of the most critical piece we found in this whole endeavor, is that there's a gap between what we could do with new technology, machine learning and whatnot, and what's going on in the field. We're lacking that historical data. BMS doesn't have historical data. You can't go back. What was the system doing that day? Nobody knows. And that's been a huge challenge. So this is, let me see. Yeah, so this is some of the data that was detected as anomalous by the system those days. And what you see is that, you see how this green line is weird? That green line is outside air. Is outside air considered anomalous? No, because it's outside air, you can't control it. And so in how much outside air was useful to do the first analysis I did because of the enthalpy, suddenly becomes completely working against us, because it's so kind of random, the outside air, that it biased all the models into thinking something was wrong while it was outside air, not something that the system was actually doing. So we had to remove the outside air from all the analysis we did and do it only on supply and return, and that gave us much, much better results. So this is a normal day. There's kind of systems behaving as it should, and then here is days that were detected anomalies because of this huge dip. So as the day begins, the systems turn on. That's considered normal. The system knows that you'll have a sharp change as the system kicks in, but then here you had something in the middle of the day that wasn't expected, and because of that, it got flagged. So now we're getting into something where nobody noticed it in the data initially, but now the system started flagging it. The last method we tried is forecasting. So the issue with the autoencoders is that it's nice, it works, but it's after the fact, right? It's like, okay, yesterday you had an issue, like it's too late. I want to know now if I have an issue. And for that, forecasting is the method of choice, because it's basically building a model and then feeding it the current data. And if, based on that current data, what it's forecasting to happen and then what's actually happening are different, then you know you have a problem. And so we started using that, and that worked really well. It was able to detect, follow the patterns really well. So it learns how it should behave based on historical data, and then new data points come in. The challenge is like sudden changes in curves and stuff, which anyway are abnormal, so it's okay. But with these techniques, the system was able to find, for example, that a lot of Tuesdays are an issue. So now we fed back the data to the engineers. Okay, what's going on Tuesday? There's a lot of them that are detected as anomalous. Let's go back and check. Let me see. Okay, so there's still a lot of work to do, but there's a lot of good things out there. And again, the main issue is that what is considered a problem. And when I say that, I mean it like really broadly, like even ask ASHRAE, what is a problematic air quality? They won't be able to tell you, right? I'm sure I ask the question here, everybody will have a different answer. What should a good CO2 level, what a good CO2 level should be, what a good PM level should be, right? So it's like, we know air quality matters, we know we have to look at it, but we don't know what's good, we don't know what's bad. And then the engineers who actually control the system are not used to that data. So there's so many kind of problems, but let's be positive. It's going somewhere. It just takes time. And I want to leave time for some questions. So quickly, conclusion. We're in a better place now than we were 3-4 years ago. A lot of people realize that air quality matters, that we need to monitor it. A lot of places start implementing it. And now the question is, how do we tie that air quality into how do we design systems? How do we say a system performs well, right? So you could say, my system performs well because my temperature is good, or do my system works well because my air quality is good, or because it works together, or because it's saving energy. So there's a lot of like those new ways of thinking how a system should perform. And I'm not commissioning or anything. I don't know anything about that world, but we hear it more and more. And then maybe the last thing is, or two things. So machine learning is are very good tools. But again, to do real good machine learning, you need to know what you're looking for. And it's not really there yet. It's still a lot of research on, really what's considered good air quality. And then the last thing, really important, is the quality of the data, right? So a lot of, I don't know, a lot of us have been used to HVAC data, energy data. Usually it's pretty accurate, it's pretty good. For indoor quality, it's kind of the Wild West. Just like, for energy, you need, if you want to do billing, you need revenue grade meters, whatever. Well, for indoor quality, it's kind of not really there yet. Everybody's coming up with their standard. Now UL came up with one, you have Reset, that try to kind of quantify how good the sensor should be. It's still very broad, and I feel like everybody could pass, but it matters. So when you pick sensors, when you do those analysis, especially for low cost, real-time monitoring, it really matters the quality of the sensors you use. And ask the questions, what sensors, what technology, how accurate, do you need to calibrate, all that stuff. It's really important. So that's all I have for today. I hope you learned something. We still have 8 minutes for questions. So, yes.
When you compare the commercial building with the school, how many sensors were you using in each one of those studies? Were you using breathing zone sensors in both buildings?
No, so for the commercial building, it was just supply air, return air on each floor, on each HVAC unit, and then outside air. And in the school, it was 2 sensors per classroom, one for like on the return air, and one just in the space. And ideally would have been also supply return air, but they were trying to figure out if they needed actually 2 sensors per room or if one was enough. And they were able to show that there was no really significant difference between the breathing zone and the return air because the classrooms are so small that they just kept them in, close to the return air because it's just easier to install than, the breathing zone. They actually tried to put them in the middle of the room, which was, a little bit disruptive, but it's interesting comparison though. Yes?
If I understood what you said early on, you were shutting the outside air off to try and, depending on the occupancy in the space. Did I understand that correctly?
No, it was the return air. The return air CO2 based on the occupancy, that's the graph I was showing. But then we were trying to figure out why the return air was so high, and it was because they were not bringing any outside air. Does that make sense? Yes?
I have a question. This data model and this machine learning and everything, how long did it take you to, once you had all the data, to develop the model and train the system? This would be one question. The other question, what kind of software did you use?
So on the software, we use SageMaker, which is Amazon Web Services machine learning tools that you can use Python and stuff like that. It's I wouldn't say it's easy to use, but training the model, the more data you have, the longer it will take, but it's not the more tedious part. The more tedious part is finding what set of algorithms work. Because, like you said, we have to try so many different things to find something that actually works. Yeah. Any other questions?
The type of sensors you were using, were they just CO2 sensors or the particulate sensors?
So there were, in all the cases, was temperature, humidity, CO2, TVOC, and then PM 0.3 to PM10. Yes.
As it relates to the comparison between the commercial and the school, I know you spoke about the quality of the sensors themselves. Despite the volume of the spaces being a little different, you can still use two different sensors as well, or you try to keep it consistent?
It was the same sensors everywhere. Yes.
On the PM sensors, you alluded to how CFM was important for those measurements. I didn't really catch how or why. Is it just the CFM? Is it a velocity thing? Or how does that factor in?
So it's a good question. So the CFM themselves. Yeah. So it's basically the CFM represent how much air comes in the space, but if you send just 100% recycled air, it's not really going to help you with your CO2. So in some cases, they're trying to, instead of using CFM, which is just how much air you bring in the space, they're trying to do fresh air CFM, I forgot how it's called, which is basically looking at actually how much fresh air you bring in the space as a percentage of that CFM coming in the space. But the idea is that if you just look at particles, especially in hospitals, they mandate, I think it's like, I don't know, I'm not an expert, it's 6 or 12 CFM, because they know they're filtering that air super well. So if there's any like virus, bacteria, whatever in the space, and you have a lot of, it's not CFM, it's air change per hour, like 6 to 12 air change per hour. It means that if you have like, let's take it simple, like a 6 air exchange per hour, in 10 minutes, the air of the room will be completely changed. So if you have something after 10 minutes, it's gone. And so that's why it matters. Does that make sense?
A little bit, yeah.
Can talk more after if you want.
Okay.
Anything else? Well, thanks so much for coming.